Hello students, welcome to EPG Pathshala. I am Dr. Aranya Bhattacharjee from the School of Physical Sciences, Jawaharlal Nehru University, New Delhi. Today we are going to discuss about a module which is entitled Lattice Dynamics in 3 Dimensions and which comes under the paper Solid State Physics. Before we begin this module, the learning objectives or the learning outcomes would be after studying this module, you shall be able to first learn the harmonic approximation as applied to understanding the lattice dynamics. Also, understand the concept of normal modes of a lattice. 3. You should be able to write the Hamiltonian of the system in the harmonic approximation. 4th, you will also learn how to find out the normal modes of a 3-dimensional lattice. And finally, you will learn how to obtain the acoustical and the optical modes. To understand the properties of solids, ions are used as a basis of crystal structure. The delocalized valence electrons move in the force field generated by the lattice of ions. Much of the properties of the solids can be understood from the motion of ions and electrons. Some of the properties which can be determined from ion dynamics include lattice heat capacity, for example, thermal expansion. Now, in the present module, we will focus on the classical understanding of small ionic vibrational in a 3-dimensional lattice. The small vibrations of the ions are described in terms of normal modes. These small ionic vibrations are called lattice vibrations, and corresponding wave that is generated is called a lattice wave. Now, in dealing with ionic vibration, we will work in the adiabatic approximation, now in which we assume that the electrons remain in their ground state during the ionic motion, since the motion of the ions is extremely slow on the scale of the electronic motion. Typically, the electrons have velocities of about 10 raised to power 8 centimeters per second, while ions have velocities of about 10 raised to power 5 centimeters per second. So, what is the harmonic approximation? In order to understand lattice dynamics in 3 dimensions, we consider the crystalline lattice as chain of ions connected to nearest neighbors by springs. This is a highly simplified view of the crystalline lattice, but nevertheless, it is very helpful to understand the basic physics associated with the dynamics, provided we assume small deviations of the ions from the equilibrium position. So now we formally try to understand that what exactly is the harmonic approximation. So as you can see from the figure here, which basically gives you a 3-dimensional image of what exactly the ionic disturbance or the vibrations looks like. You see from here that in the 3-dimensional lattice, so these red balls, they depict the ions or the atoms of the 3-dimensional lattice. So the black arrows tells you the direction of the movement. So if you look at this figure, you will see that not all the ions are moving in the same direction. Some of them towards the left, some of them towards the right. So this is a typical view of one can expect in ionic lattice vibrations. So as we had sort of discuss the 3-dimensional lattice, we will assume that the small deviations of the ion from the equilibrium position. So you have to understand this, that the ions are there in a very stable positions, and the lattice vibrations originate from the movement of the ions around the equilibrium position. So we will assume small deviations of the ions from the equilibrium positions. So also the structure of the lattice as is shown here in the figure also helps to understand that another approximation is that like we sort of think that this crystalline lattice as a chain of ions connected to nearest neighbors by springs. But this is of course, I mean, like only a very simplified view of what we have for the real lattice. But nevertheless, it gives you a very good idea and gives you the basic understanding of the physics associated with the dynamics. So now under this situation, the restoring forces on the ions are linear. The assumption of a mean equilibrium position of each ion accounts for the crystalline structure of solids. The assumption of small ionic deviation from the mean equilibrium portion leads to a simple theory of harmonic approximations. These two assumptions actually connect very well with experiments. So in physics, as we all know, that whatever assumptions we do, it hasn't connected with experiments. And in fact, over the past many years, experiments have been done and which basically clearly shows that these approximations are very well suited here. So we now explicitly consider a three-dimensional lattice which possesses n atoms of equilibrium positions Ri naught and a potential energy of the form V, which is a function of R1, R2 and so on. So the total Hamiltonian of the system is written as the summation over all the ions pi square by 2m plus the potential term as discussed before as a function of R1, R2 and Rn. So the first term of this equation is the sum of the kinetic energy of all the ions of the atoms, while the second term is the total potential energy of the crystal. Since the ions we are assuming are executing small oscillations about its mean position, so we can write Ri, vector Ri is equal to vector Ri0 plus a small oscillation of delta Ri, vector delta Ri, where this small delta vector Ri is the deviation from the equilibrium position Ri naught of the ith ion. So again I repeat this, that the equilibrium position of the ith ion plus the deviation from the equilibrium position makes up the total Ri of the ith ion. Now this figure also shows you the mathematical formulation which I had just said. So as you can see from this figure, the relation Ri is equal to Ri naught plus delta Ri is very clearly depicted here, and simply a vector addition. At the equilibrium positions, that is R10, R20 and till Rn0, the n atoms actually or the n ions, the potential energy has a minimum at this point. That is, if you go back to the formulation of the potential which I had discussed, so you simply have to say that V of as a function of R10, R20 till Rn0 is the minimum. It's quite natural. Now if delta Ri is very small, then we can expand the potential energy about its equilibrium value. And remember that this expansion is a Taylor series expansion, which I'm sure you are familiar with. So the total potential V as a function of R1, R2 till Rn is equal to first the mean value at the equilibrium position V R10, R20 till Rn0 plus then we have the first term, the partial differential of the potential with respect to Ri alpha multiplied by Ri alpha. So as you can see from here that this alpha actually is indicating the three directions x, y and z, while again I is representing the which ion it is, the first ion, the second ion and so on. And then the third term is the so-called the harmonic term, which contains the second partial derivatives of the potential. So the first term, again I repeat, is the constant term, and the second term corresponds to the lowest energy state, which is a minimum as a function of the ion locations. Now remember that this the second term, that which I just said is a linear, actually goes is basically becomes zero. Why does it become zero? It vanishes due to the fact the net force on any ion is zero in equilibrium, which is very normal to expect, and hence the first non-zero term is the quadratic. So now what I had discussed in the previous slide was that the first non-zero term is the quadratic term, and all the higher order terms we ignore. And this is exactly what is called as the harmonic approximation. So the Hamiltonian in the harmonic approximation is H is equal to, again, summation over all the ions pi square by 2m, which is the kinetic energy, plus now the first non-zero term of the potential, which is the harmonic term. So now we can write this exactly in a very short form. As you can see from here, that H then is equal to, again, the sum over all the ions pi square by 2m, which is the kinetic energy, plus half of summation over I comma j. Now delta Ri dot, now remember that this is, be careful over this, dot Cij dot delta Rj. So I have written this in a very compact form, taking into account not only I and j, but also alpha, that is the all the three axes, that's x, y and z. It is contained in this. So this Cij is a three-dimensional tensor for each value of I and j. And remember this I and j are basically the position of the ions. So I could be 1 and j could be 2, for example. So Cij is now defined as the partial derivative with respect to Ri, again a partial derivative with respect to j for the potential V as a function of R1, R2 and so on. If we move along the direction of any of the three primitive vectors of the Bravais lattice, the displacement delta Ri of the ions is periodically repeated. All the points in the crystal are equivalent. The tensor Cij depends only upon Ri naught minus Rj naught, because if one displaces just two ions by delta Ri and delta Rj, then keeping all the other ions in their equilibrium positions, the resulting energy can depend only upon their relative locations. The factor Cij obeys some important symmetry properties useful for studying the normal modes of a crystal. If every ion is given the same displacement, that is delta Ri is equal to d, then the entire crystal will simply be displaced without any change in the crystal energy. Therefore, the summation over I of Cij is equal to 0. Equations of motion and normal modes, we will discuss this concept here. The dynamical 3n equations of motion from the force on the ith ion, that is the negative of the partial differential of the potential V with respect to delta Ri, leads to the following equation: m multiplied by double time derivative of delta Ri is equal to minus summation of j Cij multiplied by delta Rj. Now note that each Cij is a 3 by 3 matrix. Now this equation can be solved by plane waves keeping track of their polarization. So now we have introduced the concept of polarization here. So we assume a solution of the form delta Ri is equal to epsilon k qk into e raised to power k dot Ri naught minus I omega kt. So here epsilon k is a unit polarization vector and qk is the amplitude associated with wave vector k. Now substituting the assumed solution of delta Ri in the equation of motion gives the following equation, that is m omega k square multiplied by epsilon k. Now remember that this epsilon k which I have introduced is a vector quantity and equal to summation of j Cij epsilon k into e raised to power I k dot Rj naught minus Ri naught. So this equation is a vector equation, and for each value of k it has got three solutions. Now continuing with from the previous slide, we now introduce new tensor dk, which is equal to minus summation over j e raised to power I k dot Rj naught minus Ri naught multiplied by Cij. So you see from here that Cij is a tensor. So simply by multiplying this already existing Cij tensor by this exponential form, we introduce a new tensor dk, and this dk is in the text, popular text or the textbooks, is known as the dynamical matrix. So this equation, the previous equation which we had, can be solved. So this can be solved by rewriting this entire equation in terms of dk, and once we do that, then we get a matrix equation. So this matrix equation is quite simple to follow. So if you introduce the dk in the previous equation of the slide, the last equation of the previous slide, and taking all the quantities to the left hand side and equating to 0, you get a matrix. Because remember that Cij is a 3 by 3 matrix, so naturally dk will also be a 3 by 3 matrix. Now this, what you see here right now, is a equivalent expression of the previous equation of the last equation of the previous slide. So here, as you can see, that it is, the first one is the 3 by 3 matrix, and the multiplied by the polarization matrix. And look at this polarization matrix, which is very interesting, that each of the component of this column vector has all the 3 components, x, y and z. So it is now quite straightforward and very simplified looking equation that we are getting here. So the 3 solutions of the previously derived eigenvalue equation for each of the n allowed values of k will yield 3n normal modes. Now at this point, let me sort of elaborate that if you go back and understand what happens in one dimension, because we are dealing here with this 3 dimension case. Okay, so now you go back to the 1D case. Now in the 1D case, let's suppose that we have this n number of ions or atoms in a chain. So now you already know from your previous studies that if you have got n atoms or ions, so then there are n modes. Okay, so that basically means that you have got now n allowed values of k. But now since we are dealing with a 3 dimensional case, so it is quite natural that we have to allow for the 3 degrees of freedom along x and y and z direction. So this basically means that you have got n modes along each directions, which is 3n normal modes. These 3 solutions for a particular k can be labeled by a polarization index lambda. Okay, so now see here the interesting concept that earlier when you did 1D, you did not have this polarization concept, but now you have, because you are dealing with a 3 dimension case now, because it is more appropriate now in this case to bring in and introduce the polarization. The corresponding eigenvalues will be omega k lambda square. So we have now here another additional factor, the lambda value that we have introduced, the polarization index, and the corresponding eigenfunctions will be the epsilon k lambda, which will have 3 components: epsilon k lambda x, epsilon k lambda y and epsilon k lambda z, with lambda equal to 1, 2 and 3 for the 3 polarizations. Now since we are dealing with crystals, it is not any amorphous solids that we are dealing with crystals. We then have to apply the periodic boundary conditions. Again, let me sort of remind you that periodic boundary conditions are emerging because the crystals are made up of a periodic repetition of the basic unit cell, the minimum volume cell, or which we call it the Wignersite cells. So applying the periodic boundary condition then leads to the condition that e raised to power I ki ni ai is equal to 1, where I is equal to 1, 2, 3 for the 3 primitive translation directions, right, that is along the x, y and z direction. Also ki is the component of k along the primitive vectors ai, and ni are integers which satisfying this particular relation, that is n is equal to n1 n2 into n3. So this implies that the allowed values of k finally for the 3 dimensional case would be, that is k equal to 2 pi times in the bracket small n1 divided by capital N1 multiplied by the vector b1 plus small n2 divided by capital N2 multiplied by the vector b2 plus small n3 divided by capital N3 multiplied by the vector b3, where b1, b2, b3 are the usual reciprocal lattice vectors. So now in this slide I have this previous equation is rewritten, that is the vector k is 2 pi multiplied by n1 small n1 divided by capital N1 b1 vector plus small n2 divided by capital N2 b2 vector plus small n3 divided by capital N3 into b3 vector. Now only k values within a single primitive cell of the reciprocal lattice gives distinct solutions. So consequently we choose independent values of k which satisfies the equation which I just mentioned, and another condition, that is all these small ni's, that is n1 equal n1, n2 and n3 should be greater than equal to minus capital Ni by 2 and less than or equal to positive capital Ni by 2. So simultaneously the k has to satisfy these two equations. So independent values of k are chosen which satisfy both these conditions. Now this second condition which I just mentioned that k has to satisfy restricts the k values to the first billion zone, which is the primitive cell in the reciprocal lattice. So you see that you have a primitive cell in the real space and also a primitive cell in the inverse space, the reciprocal space, and in the reciprocal space it is the first billion zone. Therefore in the first billion zone the total number of k values is n, and there are 3 normal modes for each k value, which gives us total of 3n normal modes. The periodicity of the crystal lattice allows us to find an equivalent k value inside the first billion zone for those k values that lie outside the first billion zone by simply adding a reciprocal lattice vector g to k. So again it basically simply implies that if some of the allowed values of k goes out of the first billion zone, then they can be brought back to the first billion zone by an appropriate lattice vector g that you apply to k, and then you get back all those k values, allowed k values, inside the first billion zone. So the first billion zone is the one which is the most important, because after all the second, third and so on, they are all periodic repetitions. Now let us take a very specific case of a cubic crystal, which is the most simplest crystal that we can think of in lattice dynamics or in solid state physics. So where k points along a certain axis, and then now if you remember that we have introduced the polarization vectors, so that one polarization vector epsilon k1 points along k and the other two, that is epsilon k2 and epsilon k3, points in the perpendicular direction to k, and this is illustrated very nicely in this figure. So you see from here the direction of k is from the left to right, and on the right hand side this figure tells you that along k we have epsilon k1. So let us say that this is the x-axis. Then along the y and the z axis you have the other two polarization vectors epsilon k2 and epsilon k3. Now doing this we can say that epsilon k1 is the longitudinal mode because it is going in the direction of k. So we say that it is the longitudinal mode, while epsilon k2 and epsilon k3 are the two transverse modes. So you have got now one longitudinal and two transverse modes. Now having found out one longitudinal mode and two transverse mode, we are in a position to discuss acoustical and optical mode. Acoustical and optical mode you have already learned in the one dimension. So let us do that again in the three-dimensional case. Now let us analyze the long wavelength properties of the 3D lattice. Now from the definition of this matrix dk, if you remember, it is clear that at k equal to 0, what do you mean by k equal to 0? That it is at the center of the brilliant zone, the components of dk matrix are real. The displacement delta Ri from the previous equations for k equal to 0 is real and k independent. So if we use the special property of this Cij matrix, that is summation over j Cij is equal to 0, and we immediately get that omega k equal to 0 lambda is equal to 0 for all lambda equal to 1, 2 and 3. So you see, this is a very unique property of the acoustical modes, that at k equal to 0 the frequency is always 0, and hence this implies that these three are the acoustical branches, since the frequencies vanish in the long wavelength limit. Long wavelength basically means k equal to 0, and the remaining 3n minus 3 modes that are remaining are the optical modes. So 3 acoustical modes and 3n minus 3 are the optical modes. So once you find out the acoustical modes, the remaining ones are the optical modes that you can see. Okay, so students, now let us summarize what we have learned in this module. In this module, you have studied what is adiabatic and harmonic approximation in lattice dynamics. Of course, as we have discussed, that this we need to understand whatever we have done in the lattice dynamics. Then you have learned how to write down the Hamiltonian describing the dynamics of a three-dimensional crystal lattice. Also, you learned the concept of normal modes from the equations of motion. You learned how to find the normal modes from the equation of motion for the lattice displacement. You've also learned to obtain the dynamical matrix equation, whose three solutions will yield the 3n normal modes. The periodicity of the crystal lattice will allow us to find the equivalent k values. And also you have learned, very important, that what are acoustical and optical modes and what conditions determine which modes are acoustical and which modes are optical. Thank you.